welcome to this explainer. Today, we are going to unpack the sheer mechanical ingenuity behind mining elemental sulfur from deep, deep within the Earth. If you've ever wondered how industrial chemistry solves seemingly impossible physical challenges, well, you're in the exact right place. So think about this. How do you mine a mineral that's buried up to 3,000 feet underground without digging a massive hole? Let's start with this massive engineering puzzle, because the solution we're looking at today, known as the Frasch process, doesn't rely on pickaxes or giant open pits. Nope. Instead, it requires a high-stakes battle against heat, extreme pressure, and some serious chemical corrosion. Okay, here's our roadmap for today. 1. The underground sulfur problem. 2. Prepping the superheated water. 3. The three-pipe Frasch pump. 4. Separating the molten mix. 5. Solidification and shipment. And finally, 6. Battling extreme engineering hurdles. We're going to trace the entire journey from surface water treatment straight down into the deep earth and back up again. All right, let's jump straight into section 1, the underground sulfur problem, reaching the depths. To really appreciate the elegance of the Frasch process, we first need to understand exactly where our target is located. These elemental sulfur beds sit anywhere from 500 to a staggering 3,000 feet underground. Just imagine that kind of depth. At that level, traditional mining with shafts and human miners, it becomes incredibly difficult, dangerous, and honestly, economically unviable. We literally need a way to bring the sulfur up to the surface without sending a single person down. Which leads us directly to section 2, prepping the superheated water, fueling the process. Since we can't conventionally dig down to it, we're going to have to melt the sulfur right where it sits in the earth. And that brings us to the main driving force of the whole operation. Now, a crucial point here. This isn't just regular hot water from your kitchen tap. We are talking about superheated water. First off, it's heavily treated to remove any scale-forming salts. Then it gets heated in a massive boiler to a scorching 160 to 180 degrees Celsius. But here's the real trick. It is kept under an unbelievable 25 atmospheres of pressure. Think of it like a heavy-duty industrial pressure cooker. That immense pressure is absolutely critical because it keeps the water in a liquid state, totally preventing it from flashing into steam. We need that dense liquid thermal energy to do all the heavy lifting underground. Okay, moving on to section 3, the three-pipe Frasch pump, the hero invention. To actually get all that intense thermal energy into the ground, engineers rely on a brilliantly designed piece of equipment. Picture a highly specialized heavy-duty industrial straw. It's basically an arrangement of 3 concentric steel pipes, drilling right down into the sulfur bed. It's a pipe within a pipe within a pipe. And this right here? This is the absolute heart of the Frasch process. So let's look at the fluid dynamics to see how this continuous loop actually works. First, that superheated water we just talked about is injected straight down the outermost pipe. This incredible heat radiates out and simply melts the surrounding solid sulfur deposit. Second, compressed air is pushed all the way down the center, innermost pipe. And third, this air mixes with the liquid sulfur and hot water, whipping it up into a froth. The air lightens the load, decreasing the density of the mix, and the immense pressure from the injected water forces this molten sulfur froth all the way back up to the surface through the middle annulus, which is just the space between the inner and outer pipes. It is a completely continuous, highly dynamic loop. Which brings us to section 4, separating the molten mix, sorting the chaos. Because once that frothy, bubbling mixture actually reaches the surface, well, we face a whole new problem, untangling it. The second the Frasch well pumps that messy mixture up to the surface, it immediately enters a phase separator. Now, the separator's job is carefully splitting the mix based on residence time, basically giving the sulfur droplets enough time to coalesce and settle, along with some really precise temperature control. It gives us 3 main outputs. First, clean molten sulfur, which absolutely must be kept above 115 degrees Celsius using steam coils or heavy insulation so it doesn't just solidify and plug the whole system. Second, we get recovered hot water, which is called bleed water. And third, vented sweep air and gases, and that includes some pretty hazardous stuff like hydrogen sulfide and sulfur dioxide. The separator essentially ensures we capture the pure liquid sulfur while safely routing away the hot water and treating those dangerous gases. On to section 5, solidification and shipment, from liquid to massive blocks. Now we actually need to prep this pure, molten product for the real world. 500,000 tons. Let that sink in. That number represents the upper capacity limit of the massive surface solidification vats where the molten sulfur is transferred. These vats are enormous, open, or compartmentalized basins sitting right there on the surface. Inside these massive vats, the molten liquid is just allowed to cool gradually. This is done by ambient air or sometimes through controlled water circulation to ensure even cooling and, most importantly, to prevent cracking. Once it hardens, the sulfur solidifies into these giant, massive yellow blocks. From there, it's mechanically broken up, cut, or lifted for shipment. Depending on its final destination, it can be shipped as solid blocks via rail and water. Or, in some cases, the molten sulfur is actually shipped directly while it's still hot in specially insulated barges and tank cars. Finally, we arrive at Section 6, Battling Extreme Engineering Hurdles, the Daily Fight. Because, as you can probably guess, this entire subterranean journey we've just mapped out is constantly under threat from the harsh realities of chemistry and physics. The operators running these facilities, they aren't just out there turning valves. Engineers are essentially fighting 3 villains every single day just to keep the sulfur flowing. Those are constant heat transfer, sourcing treated water, and severe chemical corrosion. Let's quickly break these down to understand why they matter so much. First up, heat transfer. The physical nature of our target is super tricky because sulfur has notoriously low thermal conductivity. Basically, it really does not want to take in heat. This makes melting it incredibly difficult. It demands a massive, completely uninterrupted flow of superheated water at around 165 degrees Celsius just to sustain the melting process. If that heat delivery drops or stops for even a moment, the sulfur will solidify and literally plug the entire well, catastrophically halting production. Second, sourcing treated water is an absolute necessity. Remember that bleed water we separated out earlier? Well, you can't just pump raw, mineral-rich groundwater or untreated recycled water down the pipe. Untreated water will instantly cause severe scaling, fouling, and blockages in both the heat exchangers and the well tubing itself. This means engineers must carefully manage and recycle the bleed water. They have to cool it down to prevent thermal pollution before treating it to remove dissolved minerals and salts. Only then can they recycle a portion of it back to the boiler while safely discharging the excess. And the third major hurdle is corrosion. Honestly, corrosion is a relentless enemy in the Frasch process. You've got this brutal combination of high-temperature water, dissolved salts, and highly toxic hydrogen sulfide gas. This toxic soup quickly destroys standard steel. So to survive this environment, engineers are forced to use very expensive corrosion-resistant alloys. It's a daily high-wire act of continuous monitoring and applying protective coatings just to prevent catastrophic well tubing failures, leaks, and severe equipment breakdowns. Which brings us to a final thought to chew on. With thousands of tons of mineral-heavy wastewater and highly corrosive gases being generated, how will the sulfur mines of tomorrow innovate to completely close the loop? The Frasch process is an absolutely incredible display of brute force engineering and sheer human ingenuity. But looking at these intense environmental and material challenges, it really leaves us wondering what the future of this highly demanding industrial process is going to look like. Thank you so much for joining me on this explainer, and as always, keep questioning how the amazing world around us is built.